And this one here? Yeah. Okay.
You just have to be relaxed with it.
Okay, so the next talk is from Mancini from UCL, and he's going to tell us about CosmoPower.
Thank you, Francois, and thank you to the organizers of this very lovely conference. I'm enjoying it very much, and I'm sure it's going to be a very important conference for the future years. So you heard a little about CosmoPower already from David's talk earlier, and David is one of the co-authors of the paper, which you can find in the archive with all of the details, which I won't have the time to discuss. Yeah. Yeah, sure. Sorry about that. Is it any better? Any better?
Yeah, that's perfect.
Okay, great, thank you. All right, so what is CosmoPower? CosmoPower is a suite of neural network emulators of cosmological power spectra, including matter power spectrum for large-scale structure analysis and CMB temperature, polarisation, and lensing power spectra, developed having the key idea in mind of being a tool that can be used for application to future next generation Stage IV surveys. The motivation behind this is, and I'm sure this audience knows about this, is that in the analysis of two-point statistics, still even to these days, the computational bottleneck is represented by the computation by means of Boltzmann codes such as Camb and class of the power spectra, essentially. And so the idea of emulating power spectra, so replacing the call to the Boltzmann solver with some other algorithm, is not a new idea in the field, definitely. I don't claim this to be a new idea. It's been, there have been works from ranging from Pico with Benjamin's work in 2007, all the way down to nowadays with different incarnations of the same idea, using some algorithm to emulate, to learn the mapping between parameters and cosmological power spectra with Gaussian processes, neural networks, etc. Now, the motivation behind using machine learning or deep learning for such a problem is that this is apparently a very simple problem for any machine learning algorithm. Why? Because the mapping between cosmological parameters and cosmological power spectra is a very smooth one. Okay? However, I argue that this is actually a very difficult problem. And the reason for this is because we want to develop a tool that is applicable to Stage IV surveys analysis. So in that sense, the accuracy requirements on such a tool are exceptionally high. And in order to meet them, we need to develop a tool that is thoroughly tested in order to be reliable. It is flexible in order for us to not depend on a specific survey configuration. We want a tool that is as general as possible in order to be able to replace the call to Boltzmann codes. These two main aspects motivate the choice of testing CosmoPower on the full inference pipeline, which I argue is the only way to actually fully, thoroughly test an emulator such as CosmoPower. And this is also the reason why we chose to emulate, for example, for the large-scale structure analysis, the matter power spectrum rather than the data vector CL, for example, because in that case, we would be dependent on survey-specific configurations, for example, redshift distributions and other nuisance parameters which we don't want to be dependent on. As far as, also another thing is, for the matter power spectrum, we emulate the linear matter power spectrum and the nonlinear boost, the nonlinear correction. And the reason behind this is that currently we emulate the HM code prescription. As soon as other better, more accurate nonlinear prescriptions become available, we can then retrain the emulator on those nonlinear prescription, and we can still keep the linear one, because that's not going to change. For the CMB, we emulate key quantities, temperature, polarization, and lensing power spectra. All right, so in terms of how we do this in methods, I won't go into any of the details. The methods implemented are two. One is a direct neural network mapping between cosmological parameters and power spectra. The other one is another simple mapping with a fully connected architecture between cosmological parameters and coefficients in a PCA compression of the power spectra. Okay, very simple. It's all implemented in TensorFlow and written in Python. Okay, if you want to know about the details, please ask me later. What I want to show you is a few examples of application, okay, and how we tested this tool. Starting from a 3x2 point analysis of the kids' kilo-degree survey and gamma galaxy mass assembly survey we basically repeated this analysis, and you can see the comparison between red contours obtained sourcing power spectra from class and running the inference pipeline with multinest, running on a configuration, parallel configuration with 16 cores. This analysis takes approximately 2.5 hours. In blue, same inference engine using multinest, but sourcing power spectra from CosmoPower. This on the same hardware configuration. This analysis only takes actually less than 3 minutes. And the contours agree very well with each other. In fact, they're almost indistinguishable. Moving on to more recent data set. This is the latest data release from the kilo-degree survey, KIDS 1000. Again, excellent agreement between contours in red obtained with the standard Boltzmann solver and blue ones, which are the ones obtained sourcing power spectra from CosmoPower on the same 16-core parallel configuration. And the speed up factor is always approximately 50. Now, that's not the end of the story. If I were to publish this result and only this result, this wouldn't be a tool that I would consider, sorry about that, I would consider reliable for application to Stage IV surveys analysis. All right, sorry about that. Because, we noticed this in developing CosmoPower, emulators that perform well for the accuracy requirements of Stage III surveys do not perform equally well when applied to simulated configurations for Stage IV survey. And that's how we test CosmoPower for that type of applications. We simulate a Euclid-like cosmic shear analysis. Okay, so basically configurations such as you can find on the Red Book. Is this one here? Yeah.
Maybe we'll try another micro.
Okay, I'll just carry on for now. Yeah, oh, this one here. Sorry about that. Okay, good. So I apologize for the slightly busy plot, but actually one of the main points of showing this plot is to emphasize that these emulator-based approaches are very much needed as we move towards analysis of future surveys, where the parameter space is going to be very, very large. And really, these emulator-based approaches will make the difference between feasibility and infeasibility of the analysis. So here we are analyzing a bunch of cosmological parameters, as well as a whole bunch of astrophysical nuisance parameters for redshift distributions, intrinsic alignments, and so on and so forth. Again, the contours obtained with class and with CosmoPower agree very well with each other. And this time I ran the inference analysis on a 48 cores configuration. For Euclid, it takes approximately, for using class, it takes approximately 6 days to complete, whereas using CosmoPower, it just takes less than 3 hours, actually. And importantly, there is no need to retrain any emulator. All the plots I've shown you so far have been obtained using the same matter power spectrum emulator, which I trained once and for all the different surveys, because we don't depend on any survey-specific detail, like redshift distributions, for example. Now, the next step is to really fully exploit the fact that we have a pure TensorFlow-based implementation of an emulator to integrate it with an inference engine, which is also built in TensorFlow. And so that's what I did here in this Planck 2018 joint temperature and polarization analysis. I rewrote the Planck likelihood in pure TensorFlow, essentially. And so in this case, as I'm sure you know, the Planck analysis, the Planck likelihood is very slow. It takes a long time to run. So on an 80-core configuration with MCS sampler and sourcing power spectra from class, it takes approximately 30 hours to complete. And whereas sourcing power spectra from CosmoPower, having rewritten the likelihood in pure TensorFlow and running on a sampler, which is basically a pure TensorFlow sampler, a version of MC for TensorFlow, this just takes 10 seconds on a single computer GPU. Oh, yeah, thank you.
Just turn it off. Take it off, you can use the microphone.
Yeah.
Oh,
all right.
yeah, sorry.
Right. No, I'm sorry. Okay. All right, so, and it just takes 10 seconds on the GPU, which you might have on your laptop, or you can find on Google Colab. All right, so this, I think, makes really the case for developing this type of emulator-based approaches for two-point statistics analysis. But perhaps even more convincing is the case that I'm going to try and make it now, moving away from lambda CDM, where we know that the theoretical predictions for power spectra are even more expensive to compute for a Boltzmann solver. So that's what I investigated in this paper with Alkistis, Purtsido, where we reanalyzed the KIDS 1000 cosmic shear dataset, so the latest KIDS dataset, assuming an interacting dark energy model with interactions allowed between dark energy and dark matter. The paper is, by the way, is very recent, is out on the archive last Friday. And so we trained CosmoPower to emulate matter and CMB power spectra predictions, and then used it to get cosmology results. We do find a slight alleviation of the tension in the omega S8 plane, but it's not statistically significant. The real important takeaway here is that in order to validate the emulator, we repeat essentially the testing on the Euclid-like configuration. Essentially the same configuration I showed you before, except we also have two additional cosmological parameters for the interacting dark energy model. And again, excellent agreement, but also what I wanted to point out is that on the same hardware configurations with class, the analysis takes now approximately 5 months to run, whereas with CosmoPower you can get the same contours essentially in around 9 hours. So I think this is really convincing case for developing this type of emulator-based approaches, and I hope I've convinced you that CosmoPower is a very thoroughly tested tool at the inference level. I didn't have time to comment on the evidence testing that we performed, which is arguably an even more stringent way of testing an emulator. It's staying in very large parameter ranges. The speed up is massive, many orders of magnitude. It's a flexible tool. We do not depend on the specific survey configuration. And there are other details I won't go into now, but please ask me if you're interested. Just want to mention this is compatible with all the commonly used samplers, Cobaya, MontyPython, etc. Importantly, to conclude, it's a fully differentiable library, of course. And in fact, in my future research plan is to transform it into a fully differentiable library for cosmology, including higher order statistics, beyond limber approximation calculations, and so on and so forth. So if you're interested in collaborating, please do let me know. And thank you so much, and I look forward to answering your questions.
Thank you, Alessio. So while people in the audience think about questions, we already have one online asking whether the PCA was part of the architecture of the model, or is it done separately?
No, yeah, it's done separately, right? So you compute the PCA coefficients, and then you train using them in the training process, yeah.
Okay. Any questions from the audience? Oh, okay, we have one.
You chatted a lot about the success. Is there like what's the limits of the parameter range that you allow yourself with
right.
CosmoPower?
Of course, there's always limitation to everything, right? So in terms of parameter ranges, assuming you don't change the cosmological model and you are fine with analyzing two-point statistics, I don't think there's really anything you can say against this. However, of course, there is not the flexibility of a Boltzmann code where you can change the parameters, etc. But for example, I spent a lot of time allowing people to go back and forth from derived parameters, which was kind of a limitation of previous methods. You could only sample, for example, in LNAS, and if you wanted to get constrained on sigma 8, you had to basically rerun the chain, right? Whereas now we have Gaussian processes implemented in the pipeline that can give you a sigma 8 from your chain in less than a second, basically. So, yeah, it depends on the cosmological model you consider. Now, if you change the cosmology, then you need another emulator, of course.
Okay, thank you. We have one last question.
Yeah. Hi, it's Pablo Lemos. Hi, Alessio. Great talk. Yeah, I just wanted to ask a couple of questions. One, do you test things like a summary statistic, like the evidence on the chains? Because that's a good test to see if the tails are being kind of reproduced.
Yeah, in terms of evidence.
Yeah.
Yeah, we tested the evidence. Evidence values are in great agreement between contours with class. And in fact, as you said, this is a very stringent test, right? Because you need to know the tails of the distribution.
That really does get the tails, yeah. And another question, is there a way to test kind of the differentiability aspect, that it's not doing strange things? Because Camb or class are kind of inherently non-differentiable because you have step functions and stuff built in, right? So
if you use AutoDRAD with TensorFlow, you get the gradients automatically, basically, right?
Right, but like, is there a way to check that you're kind of like not getting strange things? I cannot think of the top of my head how you would do that, but
we haven't done this explicitly, but yes, you can do it, yeah.
You can do finite differences and check that.
What's that?
You can do finite differences and check that it matches the
yes.
graph. And you find sometimes a few surprises. Exactly. Thanks again, Alessio.